morning. Good morning, everyone. Thank you for the kind introduction. As the other speakers have said, I will also say it's my great honor and pleasure to be with you. And I'm very excited to provide this talk. As my students would tell you when I lecture in health informatics at Michigan, I like to have an interactive session. So I will ask you a few questions, and so please be ready for that. You may have to raise your hand, or you may have to answer the questions. So please don't let me catch you by surprise. So let's start with a very easy question, so you can understand what I mean. So how many of you have ever used the World Wide Web and gone to a website? Raise your hand. Okay, now I think everybody has their hand up, right? All right, this is a very easy kind of question, but it keeps you engaged. Now, another question for you is related to my talk. The talk is, what are knowledge objects, and why do we care? Why should we bother with them? And so, is the World Wide Web, with all of these websites, is it a database? Is it a database? That's my question for you. Is the World Wide Web a database?
Yes.
It is a database. Okay, so we have one who says it is a database. Why do you say it's a database? It's all about information. It's an information resource, that's for sure, right? So we can think of the World Wide Web as a database. If it's a database, it's a very large database. Would you agree? It's a very large database. Okay, here's why I'm starting with this. Because you all know websites. You all use the World Wide Web. We know it's very large. And I want you to have in your mind, throughout my talk, I want you to have in mind some very large information resource like the World Wide Web. Okay? For this talk to work, you need to be thinking about large resources at scale. Not one website, not 10 websites, not 100 websites. The World Wide Web is how many websites? Hundreds of millions of websites. Okay? So my talk will work much better if you're thinking at the scale of millions and millions of knowledge objects. Does that make sense? I hope it does. Okay, so a little bit about me. I've just been introduced, so I won't go over the left side of the slide. Other than the last part here, my scientific work is not in genetics. It's not in pharmacogenomics per se. I am working on knowledge infrastructure. So my informatics work is in knowledge infrastructure, and I'll talk about what that means. And of course, I work with the team at Michigan, led by Dr. Charles Friedman. So it's been a very good morning for me. We had a talk from Dr. Friedman. We had an outstanding biomedical science talk, and now I get to follow up and talk about how do we put all of this together? How do we put what Dr. Friedman is talking about with the learning health system together with outstanding bioscience research and ultimately try to improve care? And so that's what this talk will be about. So Dr. Friedman leads our group. As you can see, I have several folks who I work with. We build software in our group, and so many developers are listed here, and I work with also many faculty members in this group at the University of Michigan, faculty from the College of Medicine, faculty from the School of Information, and I will just point out, if you don't know the name, Doug Van Houweling, who's listed there, is in the what we call the Internet Hall of Fame. And so we're working with people that helped create the standards for the original World Wide Web, the original Internet, because again, we're thinking at very big scale. Okay, so my outline for today, we're going to talk about packaging knowledge for the learning health system, digital packages of knowledge. And so first, I'll walk through an argument why we need to package up knowledge in a new way. And then talk about what a knowledge object is, and I can already tell you from just the outline, you'll get the picture here. We're going to talk about the knowledge object as a kind of package for computable biomedical knowledge, for algorithms, for code that represent some biomedical knowledge. Why must we bother with these new packages, these knowledge objects, or something like them? So we are putting out, from our research group, we are putting out into the world a concept, and of course, that concept will be improved if others compete with us to come up with the best possible knowledge object package. And then, of course, we'll save a little time. I know we're a little behind time, so I'll try to speed up, but we'll save a little time for questions, and I will attempt to give some answers. if I can. Okay, so the need to package knowledge in a new way for the learning health system. Okay, here's a quote from a writer in the 19th century. So his name is Henri Haggard, and in a book he wrote this short quote, how little knowledge is acquired in this life. We gather it up, we gather knowledge up like water, but like water, it runs between our fingers. Okay? So think about this picture and these words. There's knowledge all around us. We need to gather it up. We need to organize it. But some of it is getting away from us, right? Some of it is falling through our fingers. It's getting out of our mind. We can't remember it all. And so this is the image. So this is from the 1880s. This was written. Okay? So one of the things to point out here is that the challenges that we're having in knowledge organization for the learning health system are not new challenges to humanity. These are old challenges. But we need to think about them in a new way. All right, let's flip that around and move up in time. So John Seely Brown and a co-author, Paul DeGood, they wrote, much more recently, in 2001, the same knowledge in the world can appear both sticky and leaky. It seems fruitful to look to the context or the environment in which knowledge sticks or in which it leaks. Okay? I know this is kind of strange language, sticky or leaky knowledge. Now the hands have been flipped over in my picture. See if I can figure out the pointer. Now the hands have been, and remember, in this picture, knowledge is water. And so here, some of the water is sticking to the hands, it's staying around, and some of it is still getting away. So some of it sticks and some of it gets away. This is the human condition when it comes to knowledge, I would argue. Now John Seely Brown, if you take a quick look in Wikipedia, you're going to find that John Seely Brown has been a prime mover also in the development of internet scale innovations. And he also has a connection to the University of Michigan, so from time to time we have him come and give a talk. All right, so let's think about knowledge in the world. Knowledge in the world. So what is a textbook? So for this talk, I would argue in biomedicine, a medical textbook like the one you're seeing is perhaps the world's third slowest evolving example of sticky, leaky knowledge. Okay? Third slowest evolving example. Third slowest. Okay? It's a textbook. So it takes a long time to write a textbook. As soon as the textbook gets published, it's out of date. We all know that. It's slow to evolve. Now it's sticky and leaky. The knowledge sticks to the pages of the textbook. It's there. And when we read it, it kind of leaks out into our brain. That's what John Seely Brown means by sticky, leaky knowledge. We have to have a place where it sticks. We have to have a place where we put it. In this case, we put it in a book. But we also have to have a mechanism to make it move. We have to have a mechanism to make it flow. That's the leaky part. So I like those words because they're evocative. But what we're really talking about here is the storage and the movement of knowledge in the world to support a learning health system. Storage and movement. Okay? Sticky and leaky. All right, who wants to guess if this is the third slowest example, a textbook, what is the second slowest example? Anybody want to take a guess what it might be? Textbooks move pretty slowly.
Bible.
What's that? I didn't hear it.
Bible.
Bible is kind of important. So that's a good thought. I like that thought. I came up with my own thought, which is we'll just carve our knowledge onto a stone. So there's a thing called a stela, a stelae, and so we could just carve our knowledge onto a stone, and we'll just keep it there, and it will stay around a long time until the stone. Two things can happen to that stone. If it's the Rosetta Stone, someone can take it and they can make a floor out of it. And then we can find it hundreds of years later, or something like that, or they can use it in a building. Otherwise, we can just have erosion and eventually erode away our knowledge. Okay? All right, so the stone, maybe the second slowest, the first slowest, probably in human history, is painting our knowledge on a cave. Okay, so there are cave paintings around the world, and this is someone is trying to tell us that there's a way of hunting this beast, and this is how to do it. Okay, here's an image from a cave painting in Altamira, Spain. This is an ancient, prehistoric cave painting trying to have humans share their knowledge with other humans. Okay? And the only problem with this mode is we need to find a lot of caves if we're going to keep all of our biomedical knowledge in cave paintings. Okay, so that may not work. All right, so we're thinking about ways that humans have put their knowledge out into the world so other humans can use it. Textbook, carve it on a stone, paint it on a wall. So here's something interesting. At the University of Michigan, recently, we spent $55 million and we opened up a new library, new biomedical library for health. If you're a medical student at Michigan, you get to come to this wonderful building. This new building is a health library. Now there's something interesting. There are no books. There are no books in our $55 million library. Okay? That little thing in yellow at the bottom, I put it in bigger text there. What it says is the nearly 520,000 books that we have for the health sciences collection now resides off campus. What they're really saying is they put it in a warehouse. Okay? And if you want one of those books, you go to the library with no books and you ask them to go and get it from the warehouse, and they will go get you the actual book. But for the most part, you don't need it because they've scanned the book and you can just read it online. Okay? So a library no longer has books. Now, my office is not in the library, but it's close by. So we work right behind this library with no books. And we work with the librarians in the library with no books. And so this is an important point. We've reached a point in medical education where large institutions that teach many physicians have decided it's no longer necessary to have printed books available to their students. Everything online. Okay? So here's a research question for today for the Learning Health System. What will be the new package for biomedical knowledge? And I'll give you a hint, it's not a textbook. What will be the new package for biomedical knowledge that will have the particular properties that that package will need to allow knowledge to accumulate effectively and to flow effectively through the world, sufficiently to support continuous, virtuous cycles of learning for the learning health system. Okay? So this is a research question from information science. This is the kind of research question I'm being taught to work on and to answer as an information scientist, formerly a pharmacist, now a pharmacist informatician. So my research has this character to it. We're asking questions like this, related to the learning health system. All right, we saw this slide earlier. Dr. Friedman made the point that we think of knowledge as very important in a virtuous cycle that is intended to support learning. So once we study data, and once we generate some new insight and knowledge, if that knowledge within a community is thought to be sufficient to improve practice, we want to quickly move that knowledge into the world and inform practice. We want to change practice. Okay? And this red part, this knowledge to performance or knowledge to practice part, this is where our work is. Now, there's knowledge coming into the world, and we're trying to move that knowledge into practice. All right. So, at a high level, to begin down this journey of what is a knowledge object and why do we care, why bother with them? Of course, today we're used to PDFs of articles, and many of our slides in this talk, in this conference, excuse me, we take a picture of the article and we show what it looks like in the journal, and it's all digital. Okay? It's all electronic. Like the one I have here. There's a prediction model for lung cancer screening. Okay? And if we know in this model from this paper published in 2013, New England Journal of Medicine, if we know 10 facts about a person, then there's a pretty good AUC, there's a pretty good R-squared, and we can come up with a reasonable prediction of their 6-year risk of lung cancer. Okay? That's the current state. The knowledge is written up in our journals so that humans can read it. It's in words and pictures. We put it in libraries. Today we put it online as PDF files. You can get to them on the web through a website. In the future, what we're anticipating, the infrastructure that we're creating to support learning health systems and make knowledge flow effectively enough, is fully computable forms of biomedical knowledge. Algorithms, code, representations that are logically consistent, and that in some cases will re-represent knowledge that's already in the world, like this paper. Is that working? Yeah. So this paper already exists in the world. We can represent the model in that paper in a computable form. We call that computable biomedical knowledge. We can package that in a knowledge object. That's the work that we're thinking about. We don't believe these knowledge objects need to, we don't believe they should, replace knowledge written for people. It's human readable papers, but we do think they should complement them. So it would be nice if a year from now, 2 years from now, when a paper gets published with a predictive model, that you get the paper and you get a link to an object that has a fully computable form of that model that you can run on your own computer just by putting in some data. That's what we're thinking of. Okay? That's what we're thinking of. Complementing the papers with the objects, the knowledge objects, which are shown here on the right. So we're infrastructuralists. We think about infrastructure. That's why I started today by asking you to think big. Think about the World Wide Web. Think about how big it is. And think about how many millions and millions of websites there are. We want to think about infrastructure at that scale. So this learning cycle, this virtual cycle of learning for the learning health system, what we're doing in our lab is we're thinking about, okay, how do we begin to build components, software, tools, utilities, they go by a lot of different names, that will ultimately provide an infrastructure to support rapid cycle, successful, high impact, continuous learning for improved health. We're thinking about it from an infrastructural perspective. We want to build infrastructure, better and better infrastructure to support this. That infrastructure will need to help us create and represent computable forms of biomedical knowledge. We believe it will need to help us manage and steward, protect, preserve that computable biomedical knowledge for a long period of time. We believe that infrastructure will also need to help us apply quickly that knowledge in the world. So we want to be able to deploy computable biomedical knowledge much, much more quickly than we can today. In today's electronic health record systems, yes. In today's research and analytics systems, yes. In today's lab and radiology systems, yes. All of the systems that we use in health and healthcare, we ultimately want to be feeding more and more knowledge into those systems more and more quickly. That's the goal. That's the infrastructural goal. If we look a little bit more carefully at this infrastructure, now I'm just showing you part of the learning cycle. It's the part that we focus on in our lab. We're thinking about packaging computable biomedical knowledge, CBK, for this infrastructure to work. We believe that the way the knowledge is packaged, it used to be packaged in a book. We've gotten used to having it packaged in journal articles. Now we are thinking a new package is needed. A new package that we call a knowledge object. And we believe the infrastructure that's really needed here to support virtuous learning cycles at scale will take advantage of these new packages. And we call these new packages knowledge objects. Okay? So what I'm arguing, and why we should bother, the fundamental argument here is that a new package, a new way of packaging and moving knowledge through the world is needed. Otherwise, we will not be able to scale up the learning health system as we intend. That's the argument. So what do we need these packages to help us do? What are some special properties of these knowledge object packages that are different from books and journal articles in particular? So we need them to be open for inspection, at least for those people that have access to it. We need them to be inspectable. You have to be able to look inside of them. We want them to be readable by humans, but I also said we need them to be fully actionable by machines. So that's a new requirement, which is shown here in red. And then we want to cite these objects. We want to be able to write a paper and cite the actual object that we use to process some data or improve care. And so they need to be citable, findable, accessible, interoperable. So we're ultimately very interested in a plug-and-play capability where in any health system, when these objects are encountered, if they want to begin using these objects in a health IT system or in a research system, you should be able to take the object and immediately plug it into your system and begin using it. That is not an easy thing to do. That's why it's a research project. We're trying to figure out how to do that. Of course, we want them to be reusable and shareable and traceable, replicable. In the case of science, we want the models to come along with the data set, to come along with the paper, and allow the person outside of the original research group to replicate the results. Rebuild the model from scratch if necessary to demonstrate that it was actually built in a particular way. We want these things to be certifiable and renewable, publishable, evaluable, and testable. These things in red, though, are new for these objects. Combinable so that they can be aggregated. This is also very difficult and very challenging from an information modeling perspective. But we believe that we're going to need to use lots of knowledge objects in combination. So when we build these packages, we're trying to figure out how do we build them in a way that they can be put together into aggregates, multiple objects in a collection. We need them to be rapidly updated and changeable, much faster than we're used to with papers and textbooks. We need to be able to deploy them on large-scale networks, and so on. So it's these items in red, it's these new requirements that we believe are so important that they justify the argument that a new type of package is needed. Because the current packages, books and journal articles, just don't provide these capabilities. They don't have these properties. All right, this may seem a little bit far out. I understand that. We're not the only ones thinking this way. All right, at the Mayo Clinic, they have a relatively large team and works on knowledge management. They're building something called the Knowledge Content Management System for Mayo. So they have the idea, they're packaging up knowledge in new ways to deliver that knowledge through multiple different systems. So this knowledge base here in the middle, they're trying to work out how do you package up biomedical knowledge in a knowledge base and deliver it to a whole bunch of downstream systems. So you keep the knowledge in one place and you deliver it to multiple systems. We're also trying to figure that out. At AHRQ, which is federally funded, they have a federally funded project. This is a government agency. Dr. Friedman mentioned earlier. They also have a research project that they've sponsored called Clinical Decision Support Connect, CDS Connect. And they are also working on packages for decision support rules and guidelines, fully computable forms of biomedical knowledge, They also have a knowledge base. They call it their sources. They have mechanisms, software to deliver that knowledge into electronic health record and other systems. So they're also working on the same problem. I keep a list of it's getting to be about 30 different private and public initiatives that are working on the same problem. I'm sure my list is incomplete. So if I've found 30 projects and about 15 companies and 15 projects, there are probably 2 or 3 times as many actually in the world, maybe more. These are 2 examples. Okay, so that's my argument that we need a new way to package knowledge to make it flow in the world to support virtuous cycles of learning for the learning health system. So we have a proposal. We're working on a package called Knowledge Object. Let me tell you about it. So a knowledge object, conceptually, has 3 components. So we have a conceptual model. It has 3 components. We can take knowledge in the world from guidelines, from papers, or from analytic results, from new results, like the results that were just presented, for example. We take that, that's the input, so there's already knowledge in the world. And then what we want to do is wrap that and put it in an object. And so we think of the knowledge itself, when it's fully represented in a computable form, as what we call the payload at the center of the object, conceptually. And we add an interface to the object. So the object needs to be able to describe, for people and for machines, what it can do. And that's really the interface function. So the object needs to be able to say, this is the type of question I can answer, and this is the form of the answer you will get. I'll give specific examples. To think of a predictive model. So the answer that you can get with a risk model is some risk score. And the way the question comes in is, for a person with these features, what is their risk? And the way the object performs its task is to take in those features, calculate the risk, and send the answer back out. Their risk is some score, X, Y, or Z. We don't believe that's enough. We believe that these packages need to be very, very well described with descriptive material, metadata, for them to work properly. The same way that websites get described, if you want your website to show up high in the Google rankings, you work very hard on how you describe the content in your website. Well, with these knowledge objects, we're going to need to work very hard on how we describe the content in the objects to meet researcher needs, to meet the needs of folks in health IT, to meet the needs of folks who run health systems. So this is the conceptual model. We do have a formal model of a knowledge object. So we have an ontology that would tell the computer all of the parts and pieces of one of these objects. I'm showing you our first version of this model that was created this year on the screen. We currently are working on a publication, which is ironic since we're talking about trying to do everything in fully computable form. But still, like I said, we will complement our work with publications for a long time to come. So we have a fully computable model of a knowledge object. It has various parts and pieces, and as we add to it over time, as this model improves, we are trying to build a model that will meet the needs that we have and have those properties that I described earlier. All right, there are a couple ways to think about this. I'm trying to attach our work to things you already know. So I'm going to assume, instead of asking you to raise your hand, that you already have worked with Microsoft Word documents and you've already worked with PDFs, documents that are in the portable document format. Now these standards were engineered for us. They didn't come into the world naturally. And today we have these standards, and we can send an email, we can connect these documents and send them to each other, and we do that all the time. What we're thinking about is a knowledge object model that will have similar capabilities, so that I would be able to, a year from now, when you send me an email, and you say, Alan, I'm interested in this object, you have it in your library, or you have it in your knowledge base, and I'll say, yeah, I can find that, and I just attach it to an email, and I just send it to you. Just like we would do a Word document or a PDF today. So this is one of the uses that we are thinking of. And it's an analogous story with these other types of files. So you can think of the knowledge object model that I just showed you as a new type of file with special property. All right. So here's a nice website. Many of you probably have been to this website. It's NHRI. I use the English version of it. I cannot read the other version. What does it take? What does it take to bring us a website? So right now, if I went and got my laptop out, or those of you who have your laptop, if you went and opened up your browser, you could pull up a website from all around the globe in just a few seconds time. Wireless network. Okay? How is that possible? What does it take to do that? So this is a question about the history of the internet and how the World Wide Web came about. And the World Wide Web came about because a whole host of standards, and this is just a few of them, are actually being used in the world to make this happen. So for those of us that have never built a website, don't really know these standards, it doesn't matter. We don't need to. We can just go to our browser and pull up a website. But if you're going to build a website, you're going to encounter all of these things. HTML, CSS, Flash, JavaScript. You're going to have JPEG files of images, maybe you're going to have ASCII text. You're going to rely on all of these standards. So the internet can be thought of as really a whole host of standards that make it possible to have the World Wide Web. So the internet is this packet switching network that allows files to transfer from point A to point B and to be located, and it makes our lives a lot easier. And it supports email, and it supports the World Wide Web. And another way to think about what we're working on is we're trying to come up with a new vertical for the internet. It's not a web page, it's not an email, it's a knowledge object. And if we're successful, that will mean large repositories of knowledge objects spread across the network, and you'll be able to go to some search mechanism. Who knows? Maybe it's Google too. We don't know. Something else, and you'll search, but instead of getting to a web page, you'll get to some knowledge object. This is what we're trying to build. A new standard. A thing called a knowledge object. Maybe it's more than one standard, we're not sure. What we know today is that we've formally modeled a knowledge object, and that formal model would need to be adopted by a lot of people if we're going to be successful. All right, there are lots of different types of knowledge objects. So I'm not going to read the whole table of these types to you, because I have another slide I think that will do a better job of communicating this in context for this conference. But just think about, these knowledge objects can do lots of different things. Okay? They can calculate something, they can hold a query that we want to run periodically against a data source or sources, they can hold our computable phenotypes in a ready-to-use form, they can have logic that interprets for us in a fully computable way, health guidelines, and so on. There's a lot of things we can do. But this is a better slide, I think, for this meeting, because I was here yesterday and I was just so thrilled and so excited about all the talks yesterday. And I went home and I tried not to have too much wine at dinner. And everybody who had dinner with me knows I tried not to have too much wine because I still had work to do. And what I needed to do was produce this slide. And what this slide is, I listened carefully to the talks yesterday, but with my mind I thought, I'm going to identify all of the potential knowledge objects that are mentioned in these talks and list them. So Dr. Brendler is here, and Dr. Brendler and Dr. Sham, they talked about polygenic genetic risk scoring models. These are algorithms, they're computable. Is that right, Chaz? They're computable. Yeah. We could take those, we could put them in a knowledge object, we could put them in a library, make them findable, accessible, make them interoperable, reusable. That's our goal on my team. We can make them more complex. We can add family history. We can add some new knowledge about high penetrant mutation risk. And we can get even better models. Okay, Dr. Brendler talked about that. Yesterday in the Q&A session, the idea of computable screening guidelines came into my mind. Because once you can understand someone's risk, then we want to change their screening protocol. Some we want to screen more frequently. Others don't need that more frequent screening. How do we decide? Okay, so we can put that in a guideline, make it fully computable, deploy that in a system. Okay, these are the real-world examples from yesterday's talk. Genome-based population categorization could come out of the models that Dr. Su presented. The birth-3 cohort study is going to generate lots of new knowledge. But even before the first papers are published about the new knowledge, what's already been learned about how to run a study like that, some of what's already been learned can be made fully computable and deployed in that manner. For example, the team yesterday during the Q&A, Dr. Kuriyama, Dr. Ishiguro talked about what they have learned about how to get people to enroll in a cohort study. So once we understand that, if we can make a guideline about that and make it computable, we can maybe help other people do the same thing. Atopic disease prediction models, genomic proteomic diagnostic models, and also potentially models to help people do genetic counseling, particularly because we recognized yesterday as a group that there's a real shortage of genetic counselors. So how do we give people scripts that are going to work well so they can describe what's most important for people to know during a session in genetic counseling? The computer might also support that with knowledge objects. So all of these real-world examples just from one day here at this meeting. Okay, we have a real-world example that we've been working on in pharmacogenomics. There's a group called the CPIC, the Clinical Pharmacogenetics Implementation Consortium. They generate guidelines, but today, if you go to their website, you can find a spreadsheet, an Excel spreadsheet. Better than a textbook, not as good as a knowledge object. So what we're doing is we're writing code that will take their Excel spreadsheet that is basically a mapping algorithm. If you know someone's genetic code for CYP2D6, their diplotype, then you can map that to their phenotype. So this is genotype to phenotype mapping. It's based on lots of papers that have been published, biomedical knowledge. So what they do is they have experts that get together, they build these tables. Well, we can take those tables, and we can automatically convert them to rules, put them in a knowledge object, and that's the work that we're doing right now in our collaboration with folks here in Taipei and Taiwan. Once we have knowledge objects, we're going to need to organize them. That's going to bring us to a digital library. So we've built a prototype digital library system for knowledge objects. It works like a lot of other library systems that you use. It supports search. You can find these objects, you can look them up. It's built on open source software. It's highly scalable. And we're basically taking the science of digital libraries and applying them to biomedical knowledge objects. We call that the knowledge grid library. And then there's the last mile problem. There's the interoperability challenge. And this is a very difficult problem, and we don't have it fully solved by any means. But the idea is that, time is up? Okay. I will finish quickly. But the idea of this last mile problem is that we need a way to deploy these objects in the world that we can connect them to many systems without having to do an enormous amount of engineering for every system. So we built something we call the Activator. On the Activator, you can load knowledge objects from a library. The Activator has an engine that will run the code in those objects. And the Activator provides a set of services to outside systems, which let those services make a call, make a request, score something, generate a risk score for a patient, answer some question, and then get that answer into existing health IT systems and apps. Okay? So, in a nutshell, we're trying to make it way easier to find, access, combine, and deploy biomedical knowledge in a computable form. That form that we're working on is called a knowledge object. The knowledge grid that we're building has three main parts. It has knowledge objects, it has a digital library, and it has this Activator capability, which is separate from the library, that allows you to deploy these objects and actually get a service out of them. All right, so I'm going to just show this slide. I think I've already made this argument. So why bother with these? Well, here are 4 reasons why, and I can justify all of these with papers and thinking from other folks. So we need to organize and share our very, very fast-growing biomedical knowledge base. We need to come up with better ways to take the output from big data analytics and AI and use that output. We need to keep our biomedical knowledge mostly in the open, where scientists, researchers, clinicians, patients, family members can get to it. And we believe this is needed for a learning health system. So let me go through these slides. They just make the argument again and get to the summary. So knowledge objects are a general digital package for many types of computable biomedical knowledge. Okay? They're a digital package. They're being designed to have the needed properties, such as interoperability and combinability and reusability. And it's a standard that we believe is needed for these packages, for these knowledge objects that will support this. We believe knowledge objects, or something like them, are needed to openly manage and steward and share biomedical knowledge for the learning health system at internet scale. So we're ending where we started, thinking about the internet. Thank you for your time. That's the end of my presentation.